The title of this paper is Large-Scale Demand Estimation with Search Data, and it's joint work with Tomomichi Amano and Andrew Rhodes. What we're trying to do in this paper is to propose a new method to estimate demand in settings where consumers can choose from a large set of products. So the mental image you want to have in your mind is thinking about demand in something like, say, the digital camera category on Amazon. What's very typical in this kind of setting, especially in online markets, is that consumers can choose from a large set of products. A lot of the products in the assortment are purchased relatively infrequently, and arguably, as we're growing our assortment, we tend to cover the relevant characteristic space more and more densely, which means there's going to be a lot of products in our assortment that are relatively close substitutes to each other, and hence understanding substitution patterns between those products is a first-order issue. So those things set up the key tension of our paper. The object of interest that we're trying to estimate, the cross-price elasticity matrix between products, is very high-dimensional, yet at the same time, because of sparse purchases, we have relatively little data to work with. So what we're going to suggest in this paper is to combine purchase data with search data, i.e. data on the identities of products that consumers searched before making a purchase, and propose a model that integrates those two pieces of data. As we'll argue, the search data is going to be particularly useful for two reasons. One is that co-occurrence in search is going to indicate substitutability between products. So if a lot of consumers look at two products in the same search session, that should tell us that consumers deem those products to be similar to each other. Moreover, search data is much more abundant than purchase data. In our setting, the average product is searched 30 times as often as it is purchased, and hence we have a lot more information to work with when also including search data. The basic framework we use is taken from the literature on consideration sets. In particular, we're going to assume that there is a function Vij that determines the product-specific inclusion probability. I'll define in a second how that function actually looks like in our setting. Given that we've defined the probability of an individual product being included in the consideration set of a product, the probability of a particular set of products being considered is simply the product of individual products' inclusion probabilities, as you can see here. Now, all of this is the standard approach in the literature on consideration sets and has been done in other papers. The key innovation of our approach is going to come in through a very flexible way of modeling the function Vij that drives these product-specific inclusion probabilities. In particular, the way we're going to model the consideration set process, and in particular the product-specific inclusion probabilities, is as follows. We're going to assume that the function Vij is given by the following formula. Hence, this inclusion probability depends first on price. Second, it depends on a product-specific term, a bit like a product fixed effect that allows certain products to be generally more likely to be searched. It's also going to depend on an IID extreme value error term that's largely there for computational convenience. And finally, and this is going to be the key part that I'll delve into a little bit more detail in the next few slides, we're going to allow for correlations between products through this term gamma tilde ij. In particular, we're going to allow the gamma tilde ij terms to be drawn from a multivariate normal distribution that's centered at 0, because we've already included product-specific terms through the gamma bar j term. And we're going to estimate the variance-covariance matrix of this multivariate normal distribution fully flexibly. As I'll show you later, this is going to be possible here because we have a lot of data on consumer search behavior, and hence even in a high-dimensional setting, we're going to be able to do that. The big advantage of this is that we're going to allow product-specific inclusion probabilities to be correlated in a way that's fully flexible and doesn't need to rely on observed characteristics as it is often done in the literature. So the key logic that we're going to pursue here is that through allowing gamma tilde ij to be correlated in a flexible way across products, we're going to rationalize which pairs of products are going to be more likely to be co-searched. And if a pair of products is more frequently co-searched, that's going to lead to a larger cross-price elasticity. Conditional on consideration, we're going to model the consumer choice part, i.e. which product the consumer ultimately purchases out of the set of products that she considers, based on a standard choice model structure. So here there's really nothing new. But at this point, because most consumers search 2, 3, 4 products, that is going to be a choice model that's defined over a small set of products rather than the entire assortment, which could comprise hundreds of products. Here we're simply going to let the utility be a function of price and the set of product fixed effects, but one could easily extend this framework to also allow for observed and unobserved heterogeneity and preferences over product characteristics. In order to give you a better sense of how the model behaves and how the flexibility that we allow for actually helps us to get more flexible elasticities and substitution patterns, I want to walk you through a very simple example that should give you a flavor of how things behave. So I'm going to consider here a simple market where a consumer can consider and choose among a set of 4 products. There's no outside option, and we're going to assume that the function Vij that determines product-specific inclusion probabilities has a vertical aspect. So product 1 has a higher product fixed effect in the consideration part, which means all else equal, that product is more likely to be considered. Moreover, I'm going to allow products A, B, and products C and D to be correlated in search, but there's not going to be any correlation across other pairs of products, and hence the variance-covariance matrix of the gamma tilde ij terms is going to be block diagonal with correlation terms between products A and B and C and D. I'm also going to allow for a price effect in that first stage, as well as in the conditional choice stage. The conditional choice stage itself is going to be modeled in a very simple way. For the moment, I'm not even going to include product fixed effect, but it's only going to depend on price. Now, based on this basic model structure, the co-search probabilities that result from that look as follows. So here's a matrix of marginal as well as joint search frequencies. What you see on the diagonal are the probabilities of searching an individual product, possibly together with others. Now note first of all that due to the vertical element in our model, there's going to be level differences in search probabilities, and product A is going to be more likely to be searched than product B, etc. This is what we see on the diagonals. Moreover, the products for which the gamma tilde terms were correlated with each other are searched together more frequently. These are highlighted in red. Finally, this correlation in search behavior translates into higher cross-price elasticity between products that are more frequently co-searched. So again, the correlation in model fundamentals via the correlation in gamma tilde terms leads to more co-search between correlated products, which in turn leads to larger cross-price elasticities. And hence the correlation in gamma tilde is really the key modeling innovation that allows us to capture cross-price elasticities in a more flexible way, and in a way that's informed directly by the data on consumer search. Because our model requires us to estimate this high-dimensional variance-covariance matrix of the gamma tilde terms, there's at least 2 obstacles we need to overcome. First, we need a setting where we have sufficient data to actually precisely estimate this high-dimensional object. And secondly, we need to have a computational method that allows us to back out those variance terms in a computationally convenient way. I'm going to tackle the first part first. And so, in order to understand how we back out those terms, it's useful to think about what determines co-search between any pair of products. So if we're thinking about co-search, say, between products J and K, we can think about that probability being given by the expression you see on these slides. It's the product of the product-specific inclusion probabilities for product J and K, where we're integrating out that expression over the joint distribution of Vj and Vk. And these Vj and Vk depend on the gamma tilde terms, and hence the correlation between them will influence this expression. Now, it's useful to consider the simple case where there's no correlation between the gamma tilde terms of product J and K. In this case, the joint search probability is simply the product of the marginal consideration probabilities for the individual products, because there's no correlation between them. If instead we have a positive correlation, that's going to lead to a higher joint search probability relative to what is given by the product of the marginals. Now, it turns out that the covariance terms that rationalize co-search behavior correctly are the ones that match the co-search probabilities in the data with the model predictions. And hence what we're able to do here is to essentially implement a contraction mapping in a very similar fashion to what we often do in demand models by matching market shares in terms of purchases to the empirical counterparts. Here we're going to match product search probabilities to the empirical counterparts, and the object in terms of model primitives that are driving the matching between those empirical constructs and the model equivalents are those covariance terms. As in other demand models, we also have a set of product intercepts at the consideration stage level, the gamma bar terms, and those work very similarly to standard product intercepts in other demand models, and we're also going to back them out with a contraction mapping that matches product search probabilities, the marginal probabilities, to their empirical counterparts. Finally, although I'm not going to show you estimation results from a model applied to an actual data set, I do want to give you some simple descriptive statistics from the data set we're applying the model to and show you just how rich the search data is and argue that there's really enough data there to estimate even a very high dimensional matrix of covariance terms. So what I'm going to show you here is data from an online retailer. I'm not allowed to tell you which retailer it is. We have data over a 13-week period for almost 200,000 consumers. What I'm showing here in the first column is the purchases per product over the entire 13-week period for the top 10, top 20, up to top 50 products. In the second column, you see searches per product. As I mentioned earlier, there's about 30 times as many searches for individual products than there are purchases. So a lot more search data. But more importantly, what's relevant for our model is that we also have a lot of information at the product pair level. So we want to have a lot of information on which pairs of products tend to be searched together and which ones are less likely to be searched together. And it turns out that even at that level, we do have a lot of information from the search data. In particular, what you see here is simply the number of unordered pairs, so the number of possible combinations among the top 10, top 20, up to top 50 products. If we look at the top 50 products, we have over 1,000 different pairs that consumers could combine in their search spells. Now, it turns out that even at the pair level, we have very good coverage, in the sense that even for the top 50 products, the average pair is searched over 200 times. Moreover, the number of zeros at the pair level, so the number of pairs that are never searched together, is very, very low. We only have one pair of products that isn't searched together at all once we get to the top 40 products. And finally, I think one instructive way to think about how rich the search data is the following comparison. If you just look at the top 50 products and compare column 1 and 4 in this table, you'll see that there are more searches at the pair level than there are product-specific purchases. And hence, we should have a lot of information in this model to actually draw inference at a relatively high degree of precision about the covariance terms that are driving these co-search patterns. In conclusion, what we're doing in this paper is to integrate rich search data into a model of demand. We propose a micro-founded way of modeling both search and choice. The particular innovation that we're bringing to the table here is to allow for a very flexible correlation in consideration probabilities across products. That allows us to have substitution being driven by co-search probabilities directly, rather than tracing substitution patterns back to observed characteristics, which arguably is important, especially in online markets, where a lot of things that drive substitutions might not be directly observable to the researcher. And finally, we proposed a computational trick via a contraction mapping of matching co-search probabilities to their empirical counterparts, which help us back out the high-dimensional vector of variance-covariance terms at a relatively low computational cost. Thank you so much for listening to the presentation.